Yes, so the next speaker we have is Reza Vaez-Ghaemi. Dr. Reza, he has held various positions in management in Germany and United States. He has also served as a co-chair of the ORAN XHAL Transport Working Group and has received his BS, MS, and PhD from the Technical University of Berlin, Germany. So please welcome Reza for the next presentation. Just click on the right side.
Just clicking the right hand.
Right side, yeah.
Thanks very much for the introduction. So as you see here, I'm in ORAN Workgroup 9, co-chair, and Workgroup 9 is the Transport and Synchronization Workgroup, so that is my background. I'm local actually, from Germantown, Maryland is not far away from here on I-270. What we do is actually more transport and synchronization, backhaul testing, but what we realized was that with ORAN, with open front haul, we can add more value to our customers, and that's what I'm going to talk about today. How we can use the Open RAN, especially open front haul, to help, for example, here in this case today, use case of installing open radios, right? So what we are going to talk about today is, first of all, just brief intro into the open front haul, a little bit details of what is open front haul, and then talk about different test applications that can help providers, wireless operators, but also vendors verify different aspects of open radios. So let's get started here. So first, open radio, and we talk about open front haul several times today, but this is a different way of looking at it. And like I said, I'm more like a transport layer 0, 1, 2 person, and layer 3. So what is happening in open front haul? There are two major specifications. One is the M plane. So that is, I think there is one laser pointer here, right? It's, oh, is that also? Oh, this one, right? Okay, thank you. So M plane, right? So M plane is basically the session that is established between DU and RU, and we are going to talk about today how we are going to use the M plane to retrieve very valuable information for installation, right? So that is M plane specification. Then we have the CUS plane specifications that talk about control user plane aspects of it. That's where the IQ samples are. That is really most of the packets are in this, taken by this category. And then we have the S plane, which is basically primarily PTP, precision time protocol. And as many of you know, the full timing support is strongly recommended as primary here in CUS spec. And then we have synchronous Ethernet, which is optional. And I see more and more actually vendors and operators deploying that, even here in the US, which has been kind of quiet. But SyncE is a very good complement, especially for extended holdover times. Okay, so, and this, what you see here is you see all these packets, control plane, usually are basically go ahead of the user plane packets and identify which user plane packets belong to which slot, right, in the radio frame. So that is how it works. I'll talk about why it matters in the following slide. So, okay, let's talk about different applications. Before we even get to, this is a model, and I know this is a very simple model of how an open RAM is, right? There are various different topologies that are used, but it is one model that is used by one of the operators here in the US, and there are, very simplified, it's just one DU and RU, or 2 RUs, but the reality is much more than that. But just to make the point, here, basically, we have the RU, DU, we have a router, cell-side router, hub-side router, the grandmaster, and basically, the RU is here a telecom slave clock, and these routers are boundary clocks, right? So they are operating that way. So the first thing we want to check is that the transport is working, and that could be basic things, just optical power levels, make sure there is no problem with the SFPs or transceivers that are in there, with the fiber, Then look at the signal of just frequency, that is the right single signal frequency, 10 gig or 25 gig, for example. Then basic packet counts. Just make sure there are packets on the link and bandwidth utilization. So if it is a 10 gig link, it should be several gigabytes. If you are not seeing so many packets, then something is wrong with this network, right? And then for synchronization, similar things. Just make sure there is a PTP session going on that link with master as slave and some PTP packets. So this is a very basic transport health validation. Okay, so we go one layer higher. So as I said, on this front haul, right, we have lots of packets, primarily really control and user plane packets. And there are different things that can happen. One is just make sure, first of all, that we have the right message counts, bandwidth is correct, uplink, downlink, that they make sense. But one can go even layer below. And as one of the presenters, or maybe several today indicated, the very basic thing that many operators and vendors do is just take a Wireshark and look at different packets. It's a very, or use T-Shark, some kind of macros, some kind of homegrown solutions. I'm not here to promote certain products from us, but this is a very basic thing that tool that people use. More advanced tools are coming, but this is for our marketing people to promote. So I'm just saying this is very, very basic, right? Just use that to find out, for example, here, are these packets correct? Are the control and user plane packets coming in the right sequence with the right timing, or are they missing? Any packets missing, out of order? Those kind of things you can look up by looking into the Wireshark. All right, so then we have validate the transport layer. This example, just two routers, right, that are used. So when you have routers in the network, again, this is very simplified. Usually there are like star configurations, many different aspects to it. And so what can happen, especially during time of congestion, packets could be lost or excessively delayed or jitter. So the Open RAN specifications has defined the limits for the one-way frame delay from DU to RU. In our work group, we set 100 microsecond one-way frame delay from here to here. Some vendors may have a little bit higher values, but those are the things to watch for. Make sure the throughput is okay, there is no frame loss, no excessive frame loss, that delay is not excessive. For jitter, there is no specification in ORAN. The operators can define their own. We had this discussion in ORAN with Workgroup 4, Open Front Haul, but there was no interest in defining a jitter or packet delay variation for Open Front Haul. We will see. It will probably come later. But really, we have these two. We have throughput, three, throughput, frame loss, delay. They are defined in ORAN. We have thresholds for them, and they could be verified. So this way, you know nothing goes wrong here during your transport network aspects of it, right? Especially when you have congestion, burst traffic, those things can really impair your service. Okay, so now we go open front haul, the M plane, right? So here is one example. So we have radios here on the top of the tower or rooftop, wherever, some antennas, fiber coming. And we realized with open front haul, especially with M plane, we have really a significant value that we can offer to our customers by using the M plane, right? Like the M plane has, as many know, YANG models defined for different aspects of the radio. One of them is the transceiver YANG model, and we can just poll it, and by looking at it, we can find very valuable information about the SFP in there. Not only what SFP is plugged in, we can even obtain the power levels of the SFP on top of the tower. So that both transmit and receive. That gives us a good indication that there is nothing wrong with the fiber. Macro, micro bands, some other impairments to the fiber, or maybe some connectors are loose. So this is a very basic thing that you can do already with M-Plane. Just retrieve the Young model and look at transmit and receive power and compare with the powers that you're transmitting or receiving here. Then you basically have an insertion loss. It's a very basic concept. The second way we can use the M-Plane is, there is another Young model which is called, there are different ones, but this is like the inventory or radio type information. So here we can read the serial number of the radio, software version, manufacturer. In this case, we had an emulator from Viavi, but this could be a radio from Samsung Radio, Mavenir, others, MAC address, IP address, everything, right? We can retrieve from the bottom of the tower. So this way, for example, if there is a case where the installers that install this on the rooftops or on the towers connected the wrong fiber to the wrong radio, we can detect that here by looking at the serial number. If those fibers are connected to the wrong radio, you could have sector swapping, which you guys in the wireless domain know. Once you have sector swapping, then it impacts performance of the network. So again, very basic things we can do by looking at Young models. Now, this example actually goes beyond using the M-Plane. What we are doing, this is traditional fiber measurements and fiber inspection. So some of the things we have seen actually, and I have visited many cell sites myself, and one of the things that I noticed when customers complain to us about service problems is go to the cell sites and talk with people there in the shelter or in equipment room. And one of the things that is sometimes difficult is when we come, and the first thing we check is just check the surface of the fiber, the connector. You see here lots of dirt in there, so nobody cleaned that. So that's already a bad sign. Check the inspection. So we have this logo or motto, inspect before you connect. So here, that's a very basic thing. The other thing is it could be damaged fiber. Things can happen, especially if the people who install these cables and fibers are not properly trained. And we know many of them are, they get hired from very quickly, so they don't always go through training. And that can lead to different problems like this fiber problem, or that the fiber has some problems, the macro band, micro band, basically damaged. And the other one is SFP. Or they just put the wrong SFP in the radio. Those things can also happen. The SFP should be also cleaned here. There are tools to clean them before the fiber is connected to the SFP. These problems can be actually solved by either doing inspection with tools that are available by vendors like us, or running OTDR, optical time domain reflectometry, to actually troubleshoot where the problem is. Or we can use the Open RAN. Again, there is another Young model that we can use to find out if there are problems with the fiber, right? So, very frequent problem, actually. This is layer 0 problem. Okay, let's close by looking at some synchronization. Synchronization is very important, obviously, for the service. And there are limits defined by 3GPP. Those of you who are familiar with synchronization aspects, this is from 3GPP, the transmitter specifications. The basic one is this one, 3 microseconds between any 2 radio ports or antenna ports. And that is relative TAE, time alignment error. if you measure it against the GPS, that is 1/2 of it, 1.5 microseconds. So that is a very important number. This is for category C, which you guys recognize here, and R, interband. There are lots of things, use cases with that, especially TDD use cases. But then there are category Bs that are being introduced that have much, much more stringent limits. So again, I won't go through all the details, but these are the limits defined by the 3GPP. Now, these limits are defined with reference to the antenna ports. There are limits defined at the UNI. This is the frontal port. And those are defined by ORAN. We have some of those limits in our specification in workgroup 9, but also ITUT has limits anywhere from 1.1 microsecond to 1.4 microsecond. That is the difference between this UNI and the GPS. So we have limits for all of them. And so this is my last slide basically is, how can we validate that this network is not having a synchronization problem? So a couple of things. One is to verify that this network has a proper grandmaster that is connected, configured, and the boundary clocks are also properly configured. If they are not configured properly as boundary clocks, then the radio won't be able to lock. And if the radio doesn't lock, then it won't work, right? You can't transmit. So basic connectivity testing, make sure we can reach the grandmaster through all of that equipment on the way to the grandmaster, and that the grandmaster is obviously locked itself. And then the second thing is the time error limits. That is basically just making sure, right, that we can emulate a slave, just like here, a radio unit, and measure the time error here. And that assumes that tester has a connection to GPS, which many testers like ours do. So we can measure the time difference between GPS and the time that arrives here at the slave clock, right? And if this is, for example, more than 1.1 microsecond or 1.4 microsecond, then there is a problem. It indicates that something is wrong here in this synchronization chain. So yeah, that is the main, that's the last slide here. Let me see, I think that's it, my presentation today. Thank you for your attention.
Any questions from the audience? So, Reza, now, what is the next step for this? I mean, is it experimentation or?
No, actually, we have tested that with one major operator here in the US, and about to commercialize it here. And I think there are next steps in terms of using other aspects of the ORAN, like control and user plane, which I can't talk about today, but I think this is going on in our research and development. So,
thanks again.
thank you
so much.
All right.